Welcome to Deep Dive. We're here to unpack complex stuff and, well, make sense of it for you. So I want you to picture this. Imagine a rock from Mars. But it's not just any rock. This one's different. It's covered in these weird pale spots, almost like leopard spots, against this darker reddish mudstone background. Just imagine seeing that for the first time. It's visually striking, sure, but it's way more than that. This is the Sapphire Canyon rock. NASA's Perseverance rover picked it up back in 2024. And these spots, they're not just decoration. Scientists think they're these unique little pockets, microenvironments maybe, where ancient organic molecules, the building blocks for life might have been preserved really well. So our mission today, our deep dive, is to figure out how scientists are preparing, like right now, to analyze this thing when it finally gets back to Earth. We're talking pinpointing these tiny, fragile chemical fingerprints. We'll get into the cutting-edge methods, some surprising finds already happening, all to understand how these leopard spots could hint at life beyond Earth.
And yeah, this all comes from a recent scientific report that lays out these plans. Ready to jump in?
Absolutely. And what's really interesting here, I think, is that, the samples aren't back yet. They're still on their way, eventually. But the science isn't waiting. People are actively figuring out the how. How do we analyze these things properly? And Sapphire Canyon, with those pale spots, the dark outlines, it really is a standout. The community definitely sees it as potentially critical for understanding Mars's organic chemistry, maybe its history.
Right. So it's like preparing for this incredibly high-stakes treasure hunt. On a microscopic level. And a big part of that prep involves this technique, optical photothermal infrared spectroscopy, O-PTIR. Bit of a mouthful.
O-PTIR, yeah. It sounds complicated, but the idea is pretty clever. It's an incredibly precise tool. What it does is it uses two lasers. The first one shines on the sample, just gently heats the surface, makes it vibrate thermally but subtly. And those vibrations, they change depending on the light's wavelength and, crucially, what the material is.
Okay, so heat causes vibrations.
Exactly. Then a second laser comes in and measures these tiny, tiny changes in vibration. You put all those measurements together, and you get this unique chemical signature. A fingerprint, really. So you can see the minerals, obviously, but also potentially any organic molecules mixed in there.
Which is the key thing they're looking for, right? The organics.
That's the big hope, yes.
Okay, so this leads to a really interesting practical problem. How do you practice analyzing a Martian rock when it's, millions of miles away?
Yeah, good question. You need a stand-in, an Earth analog.
And this is where the story gets kind of cool. A bit random, even. One of the researchers involved, Nicholas Heinz, he didn't find the practice rock through some big planned geological mission.
No, not at all. Pure chance. Serendipity, really. He was just hiking out in Sedona, Arizona, and he spots this basalt rock that, as he put it, just didn't look like it belonged there.
What caught his eye?
It had these dark inclusions, little patches inside the rock, and they were roughly the same size as those pale spots on the Sapphire Canyon rock from Mars. So he just picked it up, popped it in his backpack, took it back to the lab.
Oh, just like that. A hike turns into a potential key for Mars sample analysis. That's amazing.
It really is. Shows how science can happen anywhere.
But, okay, using an Earth rock, even one that looks similar, it can't be a perfect match, can it? Mars is Mars, Earth is Earth, different history, different weathering. Did they worry about that? How did using O-PTIR on the Sedona rock account for those differences?
That's a really important point. And yes, they absolutely considered that. The Sedona rock was a good visual match, mineralogically similar in some ways. But yeah, Martian processes are different. The goal wasn't to pretend the Sedona rock was Martian. It was about testing the method. Could O-PTIR actually pick out and identify tiny chemical differences within a complex rock sample, like the kind they expect from Sapphire Canyon?
Okay, so it's about validating the tool itself.
Precisely. And it worked exceptionally well. O-PTIR showed really enhanced spatial resolution. That means it could zoom in, chemically speaking, on those tiny spots individually, get clear data from just those areas. And another big plus, it's fast, super fast. You can get a full spectrum, that chemical fingerprint, in just minutes.
Minutes. Wow. Why is speed so important here?
Well, think about how precious these Martian samples will be. You don't have unlimited time or material. Speed lets you quickly scan a sample, find the potentially interesting spots, maybe areas richer in organics, and then you can target those specific spots with other, perhaps slower, but even more sensitive techniques for a deeper dive. It's about efficiency.
Makes sense. Triage the sample quickly. Focus your efforts. So what does this mean more broadly, this O-PTIR capability?
Yeah.
It's not just theoretical for Mars, right? They're actually using it.
Oh, yeah. It's already a working resource at JPL, NASA's Jet Propulsion Laboratory. It's quite unique. They used it back in 2024, actually. It was critical for the Europa Clipper mission. They used O-PTIR to double-check that the spacecraft was absolutely clean before launch, made sure no Earth contamination would mess up the search for potential biosignatures on Jupiter's moon, Europa.
Okay, so it's already proven its worth in planetary protection.
Exactly. And now that they've shown how useful it is for Martian rocks and geology in general, they're working with the Mars science teams to test it on other things, too, like algal microfossils. Scientists often use those as practice targets, Mars analogs, when testing rover instruments.
So the applications keep expanding. It really makes you think, doesn't it? How many other technologies like this are being quietly developed or perfected right now here on Earth, getting ready for discoveries we haven't even dreamed of yet?
It's a constant process of innovation, absolutely.
This has been fascinating. It really shines a light on just how clever scientists have to be to prepare for these missions. So just to recap for everyone listening, the big takeaway here is how scientists are getting ready for those Martian rocks. They're using super advanced techniques like O-PTIR, practicing on Earth rocks found, incredibly, even by chance on a hike. And it's not just about mapping minerals. It's laser-focused, you could say, on hunting for those specific chemical fingerprints, the signs of organic molecules, the stuff that could be linked to ancient life, the fact that a random rock from Arizona can help fine-tune tech for Mars, combined with the speed and incredible detail of O-PTIR. It's pretty mind-blowing stuff. And it leaves us with a thought to chew on, doesn't it? If a casual hike in Arizona can accidentally provide a key piece for studying Mars, well, what other breakthrough insights are just lying around, waiting, hiding in plain sight maybe? Just needing the right instrument, or maybe just the right curious person to notice them? And thinking further ahead, when those first real samples from Sapphire Canyon finally arrive with those strange leopard spots, what will they tell us? What will it really mean for how we understand life here and potentially elsewhere when those rocks give up their secrets?